So this is problem 2.23 from Griffiths, which says for the charge configuration of problem 2.15, find the potential at the center using infinity as your reference. So looking at 2.25, it says a thick spherical shell carries charge density rho equal to k over r squared for r between A and B. And then it wants you to find the electric field. So to do 2.3, you kind of have to do 2.15. So it's kind of a double problem, I guess you could say. So we have a shell, that's what I drew. The inside is for the radius less than or equal to A. Then you actually have the material between A and big R. And then B is outside of our sphere. So to find the potential, we can find the E field at all 3 points. And then from there, we can integrate to find the potential. So let's start for R equal to A. In other words, inside. So this is what we're going to do for all these. We'll do the closed surface integral of E dot dA equal to Q enclosed over epsilon naught. We've done this a million times. We know this will be the magnitude of E times 4 pi A squared equals, well, inside the cavity there's nothing. There's no charge. The charge is past R. So it's 0. In other words, your E field is equal to 0. So there's no E field inside this cavity. So that one's actually pretty easy. The next region we'll look at is for A less than R, which is less than B. In other words, in that this region here that I kind of filled in, we're going to follow the same general idea. The closed surface integral of E dot dA equals the enclosed charge over epsilon naught, where this is going to be equal to the magnitude of A times 4 pi R squared equal to Q enclosed over epsilon naught. Now we're going to spend a little bit of time to figure out what this enclosed charge is. So the enclosed charge is going to be the triple integral of rho d tau. The charge density, rho, which is charge per volume, times a volume element. And we know what rho is. So, and this is going to be in spherical coordinates. So this will just be from 0 to 2 pi, 0 to pi, and then we're going to go from A to R. So not 0 to R, because that's nothing. We're only interested in that particular region, which is from A to R. So hopefully that makes sense. We're only going basically from here to here. That's like our line of integration. So rho was given to us in the first problem, so that's going to be k over r squared. And then d tau for spherical is going to be r squared times sine of theta dr d theta d phi. So Q enclosed is going to be 4 pi, that's coming from sine theta d phi, times our constant k, times the integral from A to R dr. So this ends up equaling 4 pi k r minus A. So the magnitude of your E field times 4 pi r squared is equal to 4 pi k times r minus A divided by epsilon naught. And you can see your 4 pi's cancel. And then we find the E field in this middle region here is equal to k times r minus A over epsilon naught r squared in the r hat direction. Okay, so now we just have one other region which is outside of the sphere. So this will be for r equal to b. So we'll again have the magnitude of E times 4 pi r squared equals Q enclosed over epsilon naught. And we're going to find Q enclosed the exact same way we did earlier. So let me actually give myself a little bit of space. It'll be the triple integral. Same exact reason. The only thing that's going to differ here is now our bounds of integration will go, now our bounds of integration are going from A to B, because that's where our charge is. So you can think of like going from here to here. And the other integral we did earlier, there's obviously no charge inside, so there's not, you don't need to do that. So here we're integrating from A to B. And then we'll do K over R squared times R squared sine theta dr d theta d phi. So really the only trick here is to get your bounds right. If you were okay with the bounds and why we picked what we picked, then it's not too bad of a problem. And just going a little bit fast here, we end up getting Q enclosed is 4 pi k. Now this is going to be B minus A. So very similar to what we had earlier. And putting this together, you get your E field is equal to K B minus A over epsilon naught R squared and the R hat direction. So we found the E field in all three parts, which was actually this problem. So we did 2.15. We didn't plot it, but that's whatever, not necessary. Now what we're going to do is do the original problem we wanted, which is to find the potential. And the reason why we did all this work is because your change in potential is just the negative integral of your E field. So we did all that work to find the E field, that way we can find the potential. And we'll do this from infinity to the center, where infinity is our reference point. So if we do that, we'll do the negative integral from infinity to B, which is the outside part. So we're basically going in, you could think of it. So we go infinity to B, and then we can go to R, we can go to A, we can go to the center. You get the idea. That's basically the route we're going here. So we go from infinity to B. Our E field there, this was our E field in that region, minus, we'll integrate from B to A, and then that'll be K R minus A epsilon naught R squared dr minus the integral from A to our center, 0 dr, because that was our E field there. Now this is obviously 0, that's redundant. This is also 0 because that's our reference point. So the potential at the center is going to be minus K times B minus A over epsilon naught, the integral from infinity to B, R to the negative 2 dr, minus K over epsilon naught, and we'll break this up into two integrals. So we'll have R over R squared dr minus the integral from B to A over R squared dr. So I factored out the K over epsilon naught, those are constants, and then I just broke the integral up into two integrals. So this will actually simplify. That's just a 1 now. Let's see, here we're gonna do a power rule. So we add 1. So that negative will be multiplied, so this actually turns positive. And we have 1 over b minus 1 over infinity minus k over epsilon naught. This is going to be, this is 1 over r dr, which is going to be the natural log of a over b, minus a, so we could factor this a out, and this is the exact same integral as the first one, so that's going to make this a positive, and it'll be 1 over a minus 1 over b. Now this is obviously 0, so the potential at the center we have as k over epsilon naught, that's everywhere, b minus a over b, minus the natural log of a over b, plus a over a is just 1, minus a over b. And then let me distribute this negative. So what I did is I distributed this negative, and I factored these guys out. So the potential at your center is going to be k over epsilon naught. I can rewrite this as 1 minus a over b minus ln of a over b minus 1 plus a over b. And we can see the 1's drop, a over b's drop, and we get minus k over epsilon naught ln of a over b. And using our rules of exponents, I can get rid of this if I flip the denominators here. So I get k over epsilon naught is the natural log of b over a. And b over a are radiuses, so those are going to be positive. So this is the potential at the center. So this is a good problem because it forced us to find the E field as well as the potential. So it kind of worked a little bit of two things at once. And hopefully that made sense to everybody.